Okay, so if everything is going well, I'm now recording. And I will put it up on all of the screens. Hello, you're just in time.
Yes.
So Grant, we'll go ahead and get started.
Yes, guys, so thank you for coming. This is our first workshop. We're going to cover some introduction to AI, that sort of thing. Feel free to take notes if you want, or don't, or whatever you want to do.
Yes, we will.
Yeah, we'll try to do that. So let's get started. So first of all, we thought that it'd be good to sort of talk about a sort of overall map of where artificial intelligence, machine learning lays in just sort of the overall scheme of computer science in general. So this is from a YouTuber. Dana, do you remember which YouTuber made this one?
Domain of Science.
Domain of Science, very good YouTube channel. He makes a lot of maps of stuff. So this is sort of a map of computer science in general. And this stuff's really cool because it just kind of shows a lot of different sort of sub areas of computer science. So you can see sort of at the top left, you have some more of the theoretical. And top right, you have some more sort of hardware stuff. And then the bottom left, you get some of the sort of AI, optimization, machine learning, that sort of thing. But the point here is that there's a bunch of different sort of subcategories, and they're all kind of related in certain ways. And a lot of the machine learning and other stuff relies on a lot of the sort of foundations and the theoretical algorithms, that sort of thing. So I guess today we want to cover a few things. So we want to talk about how do we define intelligence in general? Because we talk about artificial intelligence, and a lot of us have an idea of what that is, but what does it mean to be artificial? What does it mean to be intelligent? These are good questions. We're gonna sort of do a survey of some different topics of artificial intelligence, and we're gonna show the sort of comparison between that and machine learning. And then there's a few sort of main subcategories of machine learning that we're gonna go over. Then after that, we're gonna talk about another branch of AI, and then we're going to talk about some current limitations, that sort of thing. So basically just kind of like a survey going over a lot of things. It's an introduction. So first off, we're going to talk about what is intelligence. And there's a lot of different definitions of this. And so two important parts are categorization and analogy. And these are kind of the ability to relate things to one another, be able to say, hey, how are these things similar? How are these, if you're looking at somebody's face and you want to recognize it's a face, then you want to say, well, hey, we have two eyes here, we have some features of this thing, this must be a face. So it's a sort of ability to sort of implicitly draw conclusions about your surroundings based on sort of sensory input. And so here we're showing some sort of examples of that. So in the top row of stuff right up there, you can kind of see how there's we can tell that there's similarities between these four images, even though that they're very different images, if that makes sense. And so that's sort of a part of the categorization analogy. Okay, so then talking about artificial intelligence and programming. So we normally do, if you do normal programming, that sort of thing, you could say that's kind of intelligent because it's sort of automatically doing things, which is pretty cool and whatnot. But when we're talking about artificial intelligence and programming, we're talking about something a little higher level than that. So I like to say that you can make artificial intelligence just using sort of if statements and conditionals, because really the artificial intelligence is intelligently making decisions or taking action based on some sort of condition of your environment. So if you think of a robot car or something that wants to avoid crashing into a wall, maybe it has a LiDAR sensor on it that will tell it when it's getting too close. And so you could have some sort of if condition, be like, hey, if the distance is less than 10 inches or something, then let's stop the car. And you could argue that that's artificial intelligence. So it's a very broad term. So some examples here are certain searching pathfinding algorithms. And so this might be if you want to, hey, if we starting from this point, we want to get to this point, how do we do that? How do we make a path for that? Other sort of searching algorithms and that sort of thing. So this would be an example of just kind of general artificial intelligence, not really deep learning per se. But this is just to kind of show that there's a lot of different types of that. So, and also feel free to, if you guys have any questions at any point, feel free to raise your hand or shout out or something.
Excuse me. Okay, so I'm just going to show off something that I made that sort of gives you an idea of pathfinding algorithms and the basics of simpler AI programs. So this is a web app I made when I was first learning web programming, so don't judge my UI or anything. But the idea is that you can create walls on your own, place a start, place an end. You can think of this as like you have an agent you're trying to get from the start to the end. And you can have informed searches and uninformed searches. For instance, breadth first search is just you go in every direction, then once you get where you need to go, reconstruct the optimal path there. Then also you have something like A star, which is a informed search, which means you know where you should be going, so you sort of prefer that direction, like this. So you can see just on the runtime that A star is a little bit faster because you know where you want to be going. Then, yeah, another example of some basic AI programs is Markov decision processes and minimax. Do you want to go over Markov first?
Sure, I'd love to. So a lot of these like really fancy like artificial intelligence and machine learning. Actually, do we have still have a slide comparing the two?
Yeah.
Okay, we do. That's later.
Yeah.
Okay. Yeah. So anywho, a lot of these like really fancy stuff have a lot of these like really sort of fundamental, sort of intuitive foundations to them. So here, if we're talking about these things called Markov decision processes. So these are based on what's called a Markov chain. And so if you look at this example here, you see there's these different nodes. And I think this is kind of modeling like a robot and its actions. So you might see that it starts at a standing state. And then these edges that are connecting the nodes and that sort of thing represent probabilities of transitioning from one state to another state. So for example here, if it starts at standing, there's a 50% chance its next action should be to take a step forward or something like that. And then from there, then it might want to take another step forward with a 40% chance, and then it might end up being in a crashing state or something. But the point is that you can kind of model these things with these kind of simple graphs. And then once you have these sort of simple models, you can really build upon this to make these really powerful models. So Markov decision processes in general are really the foundation for reinforcement learning, which is a branch of machine learning that we'll get into later. But essentially, the point is that if you have this model of different states it can be in, you can try to figure out what should the probabilities be connecting these different states in order to get an optimal sort of result or objective. So, yeah.
Yeah, then I'll quickly talk about Minimax. It's one of the more basic, it's called like an adversarial search. And the idea is that you're in some sort of environment where you have to make a decision based on the state, but each turn, quote unquote, it's actually you then an adversary. So a lot of times this can be used to represent, say, like board games. That's the most easy way to think about it. So you can see up in the top row, let's say that we are X. We can define this as we have 3 different moves. And 1, we win, and then 2, it's sort of like a non-terminal state. And so then what we do is we search down this sort of tree structure, and we sort of propagate up the scores. So we want to be maximizing, but then it gets down to the opponent, and they want to minimize. So both of these areas, they get to a node that's a -10. So that propagates up, and both of these, number 3 and 4, they will be labeled as -10. But we are the maximizing party, so we choose the 10 over the 2 -10s. And that's just a way that we can make smart decisions in like a turn-based area. You want to talk?
Sure. So we've talked about, and maybe you guys have heard about, there's artificial intelligence, and then there's like machine learning. And some people treat them kind of synonymously, and some people really only say one or the other. So we thought it'd be good to kind of show some of the differences and just kind of define them a little bit. So if you think about the history of it, artificial intelligence went kind of way back to the 1960s or something like that. when there's some smart dudes trying to make some like checker bots and stuff, because they thought that was cool back then or whatever. I mean, it's still cool now, but anyway, so artificial intelligence is kind of like the main sort of thing. And then machine learning is kind of a subset of that. So it's machine learning is a type of artificial intelligence, but artificial intelligence is not always machine learning. And so then that's more of a statistical data-driven approach. And then inside of that, we have neural networks and then also deep learning. And so deep learning is, again, a subset of machine learning, which is a subset of artificial intelligence. And with deep learning, the main point of that is that you have these different sort of hierarchical levels of understanding, and you can have these what are called like these nonlinear relationships between your inputs and your outputs. And so the point with deep learning is that because of sort of mathematical structure of the models, you can better fit and predict like more complicated stuff. So.
Okay, so yeah, giving a quick definition by Arthur Samuel, it's the field of machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. And that's by a man who wrote a program to beat himself in checkers in 1959. So either he's a founding father or he's just bad at checkers. So I don't know why that happened. Okay, so yeah, like we said, we're gonna separate machine learning into 3 different categories: supervised, unsupervised, and reinforcement. And again, this is just another visual map to sort of show where does machine learning break into, what sort of applications does it have, and we'll go more deeper into this and sort of define it ourselves. So, first of all, we have supervised learning, which in general is learning based from labeled data. So what that means is that you're given a set, many sets of input features with however many variables. And each one of them has some label, which could be continuous, just a regular number, or it could be discrete. It's like a dog or a cat. And the idea of supervised learning is we want to learn some function where we can take the inputs and give an output that best fits the data. So an example of the sort of number example is regression, which, for instance, we have many houses, and each of them have so many square feet and so many number of bathrooms, and we want to predict how much that is going to cost. So that can sort of be, that can be a y equals mx plus b sort of thing, nice and easy, or it could be much more complicated. Then another example, easy classification, see an image of a cat or a dog, is it a cat or a dog? And yeah, one of the most popular ways is to find a sort of cost function, which represents how bad your current fit is. Then using cool math tricks, sort of get to the minimum of that cost. And here's an example of that. So you can see on the right side, we're trying to get a best fit to these sort of data points. And on the left side, this is sort of like a cost function. If you're very high, you're doing very bad. But then using calculus, you can find, even in 3D rate of change, just go down until you hit a minimum. And we'll cover this a lot more in like probably the next workshop. So on the flip side, we have unsupervised, which is learning from unlabeled data, which means we only have the input, we don't give it an output, and we just want to algorithmically analyze the data to derive meaning, which is much more broad. But yeah, some examples are clustering algorithms, anomaly detection, and neural network autoencoding, which clustering you can see here. So what this is doing is we have told it that we want 3 clusters of these given data points. And algorithmically, each iteration, it makes these clusters more and more distinct. So what we're doing is we're saying, just take this input, categorize it into 3 different places. It doesn't have to know if that's a picture of a cat or if the x-axis is price, y-axis is like willingness to buy, or whatever. It just, you put in the data, you want to get some information out of it. Then, Connor, do you want to talk about reinforcement?
Yeah, sure. So conceptually, reinforcement learning is quite a bit easier to understand than supervised or unsupervised learning. The terminology is borrowed from psychology, and as you can imagine, it's just sort of an agent that is learning to do a certain behavior over time. So we have an agent that is in a certain environment, and we'll see an example of this in a moment. We have an agent in an environment, and it reacts or interacts with that environment through actions. And this will result in a certain reward defined by our reward function. And so our state represents the state of the agent in that environment over time. So
And there's an example of that.
yeah. So here's an example. So in this case, our agent is this sort of stick man in this sort of environment with these obstacles. And so its state would be represented by its position, what its sort of movement is at the moment, where its legs are at, and so on, and sort of what obstacles are in front of it. And so over time, it'll experiment with different behaviors, and based on our reward function, so our reward function receives the agent's state at a given moment. So if that state looks something like it's on the ground and it's not moving, then we're obviously not going to give it a high reward. We're going to penalize it for doing something like that. If it's doing something like it is here, where it's sort of moving fluidly and overcoming these obstacles, then we would give it a higher reward. And so over time, its good behaviors will be reinforced, and it will learn to overcome these obstacles.
Okay, so then this is I think it's one of the last branches we're gonna cover today, but this one is called meta-heuristics. And so this is a somewhat distinct branch of artificial intelligence that almost falls into the realm of optimization a bit more. So just to start, we're gonna talk about maybe like what's a heuristic before you figure out what a meta-heuristic is, you know? So here's some definitions I found on Wikipedia. But basically, heuristic is essentially something that can guide a search to find the optimal solution. So say you're trying to, in the pathfinding example, so the first example he showed was not super good. It just kind of spread out from where its origin point was. And then once it eventually found it, it found it. But the second one we could say was heuristically guided because it made its sort of searching behavior based on whether it was getting closer to its objective or not. So if you say heuristic, again, it's a way of solving it more quickly as opposed to sort of just kind of brute forcing it. And so then a meta-heuristic, then they say that's a higher level procedure or heuristic, sort of designed to find, generate, or select a heuristic. So this is something that's like a bit at a higher tier than a heuristic. It can kind of not only solve the problem, but figure out how to solve the problem, if that makes sense. So there's a lot of one of the reasons I really like this is there's a lot of really cool algorithms derived from this, and a lot of them are really nature inspired, which I think is super cool. So this one is called ant colony optimization. So here you can imagine this is literally just like some ants trying to find some food or something like that. But what this can represent is trying to find the absolute or a local or a global minimum of some sort of cost function that would allow you to best produce a behavior or something. And so this one is, again, nature inspired because some researchers or something were studying ants, and they found that when the ants were trying to find food, they would initially just kind of spread out all over the place, but then they discovered that the ants would sort of drop these like pheromone scents and that sort of thing, and that they would actually be able to guide the following ants to sort of all try to find food together. And so as you can see with this animation here, they start on the top left or whatever, and they're all sort of scattered about, and they're all searching in different areas. But then once they are sort of getting close to the solution, they sort of draw them into each other. And so this is sort of a way of searching for and finding a solution. And so there's a lot of other cool ones too that are based on like sort of bee hive behavior and just sort of like a swarm intelligence in general. So next I want to talk about genetic algorithms. And this sort of falls under the branch of evolutionary algorithms. So these are, again, kind of nature inspired, which is cool. So imagine you have a little stick man again and you want to get him to walk. You can sort of model the walking as a group of different angles between the joints, right? And then what you can do is you can model each parameter of the joint as sort of a genome. And so then if you want to have something that controls the walking or something, say you have some mathematical function, like sometimes they use neural networks, but you could really just use some sort of basic mathematical function to basically predict what the angle should be based on the inputs, which could be the other angles or how far it is from the ground or something like that. But then eventually what you can do is you can make this sort of population-based algorithm. So you can basically spawn like a bunch of these stickmen with different like randomly initialized parameters and that sort of thing. And then what you can do is you can have them all try their best at walking, and then after they all fall over or die or whatever, you can pick out which ones did the best, and then what you can do is you can cross over their genomes, and then that sort of lets you naturally select for a more fit population. And then if you do that iteratively, then eventually you kind of evolve a solution to that problem. Yeah. And so then some other stuff, some sort of like worth mentioning. Natural language processing is another like really big branch, where essentially it deals with either text input or voice input, stuff like that. So we'll probably go over that at some other point because that's a pretty big branch. But do you want to talk about some limitations maybe?
Maybe
Oh,
not.
okay.
But I can go back
No.
to the stuff I missed earlier.
Yeah, no worries. Okay, so there are some serious limitations of artificial intelligence, stuff like that right now. I guess just kind of going over a little bit of how it's evolved, because I think we dropped that slide for some reason, maybe. Do we have that slide still?
I don't know what you're talking
Okay. Well, we're going to go over into a little bit of history, I guess, of it. So artificial intelligence, I guess computers in general started being theorized in like 1920, something like that.
Yeah. Charles
Um,
Babbage was even earlier, like 19th century. But
Oh, wow. Yeah, so, I mean, eventually, first of all, computers were sort of inspired by more mathematical things, like the Turing machine, which is the sort of foundation for a lot of, like, the theoretical foundation for a lot of computers, was originally like, sort of constructed to make for like a mathematical proof. So, anywho, back then they were like all super big into like math proofs and stuff like that, and so then they sort of accidentally made a computer theory model sort of thing. And so then in like the 1960s and that sort of thing, they start saying, well, hey, how can we make these machines like more intelligent and stuff like that? Because I think Turing in particular had a paper or something in like 1940s or something where he's like, well, hey, what's the limit of these machines' intelligence and that sort of thing? So in the 1960s, they started doing that. But at that point, the hardware for the computers did not have nearly enough computational power to really do anything. So they'd have these like really big machines that could only do these really simple things. So they had like a whole room that was trying to, I don't remember exactly what it was doing, but it didn't do it that well, and it was not really worth it. So it kind of died down a bit then. I think then in the 1980s, perhaps, they sort of revived it a little bit, and like we're looking into it a bit more because by then they had more powerful computers. And they actually figured some stuff out then, so they started using it. But it couldn't quite model these really complex problems well. So then around the 2010, that's kind of when the deep learning was introduced. And so then at that point, AI sort of really exploded because we have the computational ability to do cool stuff in real time and other stuff like that. So, but in terms of limitations right now, so I mean, again, I'm sure computers will get more powerful in the future, and that will enable us to do more stuff. So I guess the power of computers is one limitation right now. Then, I mean, I'm sure that we can find some more interesting, better algorithms in the future, I guess. And then I guess another interesting point is that in the future, especially as these get more powerful, people are going to have to sort of consider the ethics behind these models. There's a current model called GPT-3 made by OpenAI, and they're basically not making it open source because they're afraid people are going to abuse it and use it to like make like sort of hate chat and stuff like that, I guess. So another limitation is the limiting access to stuff, which could be good in some ways, but then it's not as good in others. So yeah, do you want to talk about the other stuff?
Sure. So yeah, I was gonna do a little cognitive science sort of prologue, but I got locked out. Um, but anyways, so when we're thinking about artificial intelligence, it's quite useful to understand like human intelligence or intelligence in general. If we want to define artificial intelligence or examine what AI's goals are or the sort of techniques used in AI, it's a lot of that relates to human intelligence. So what is intelligence is a pretty, it's a large and involved question. But when cognitive scientists basically try to boil this down to its fundaments, we can sort of mainly examine categorization and analogy. So one big question is what happens when we're trying to learn? Obviously, this is an important question when we're considering machine learning. So let's say you're a visual learner and you're a beginner programmer and you're trying to understand the concept of a loop. They've made it pretty easy because the name itself is an analogy to this thing that sort of starts where it ends. But if you have that image in your head of a loop, then that can make it quite easy to understand this thing in programming. And once you've sort of established that knowledge, that becomes a category that is sort of in your sort of brain storage that, similar to a loop, you can draw on when you're trying to learn other things. So if you are trying to learn about summations in math and you understand loops very well, and this becomes quite easy because this is just a loop from I to n, where we do what I've just described here. So analogy is really the core of cognition and how we learn and how we build models of external reality. So when we're trying to teach machines to learn, that can seem like a kind of a difficult thing to do. It's something that happens very naturally with humans, but maybe a little less intuitive when it comes to machines. But if we look at this example of unsupervised learning, so this is just a sort of basic cluster analysis. So let's say I went out and I got a bunch of leaves and I didn't really know what trees they belonged to, but I got a bunch of leaves, I measured their lengths and widths and plotted them. Here it's very easy for humans to recognize three distinct clusters. And we can draw ellipses around them and say that these represent 3 trees, and every sort of point that falls within this cluster belongs to that tree. So here we are categorizing using some sort of simple statistical procedure. And we can make judgments based on these categories. So we can say that leaves that belong to the tree from the red group are more varied. There's a much sort of wider range here, whereas trees or leaves from the blue or green groups are more consistent. And we can also use this to make judgments about new phenomena. So let's say we get another point and it falls pretty close to the green cluster, then we can sort of analogize what we know and with this new thing and say that this belongs to the tree represented by the green group. Or if it's way out, maybe we need a new category to represent this sort of new thing. So this is a simple statistical approach that mirrors the core of human cognition in a lot of ways. And what we're trying to do a lot of the time with machine learning and artificial intelligence in general is find mathematical approaches or models that do the sorts of things that human intelligence does very well. And then this here is a little different. When I was talking about analogy just now, I just sort of meant relationships. This is sort of more the classical A is to B as C is to D thing. But I thought it was interesting. Basically what they've done is they've trained this neural network to take 3 images. So basically if you imagine A is to B as C is to D, at the top you've got this image is to that image, so then we provide this new image and it comes up with that one. Or with this one, they say this image is to this image, so now we swap these blue and tan circles, and then it does the same thing here. it's kind of not exactly related to the analogy I was talking about before, but I thought it was interesting. It's from the NYU Image Analogy Project, so I wanted to include it. So yeah, that's what I.
Okay.
And then also one more thing is, we talked a lot about the theory here, but I was thinking, would it be useful just to kind of go over the main topics again and just like give a little brief blurb of like when you might want to use this or something? Would that be good? Okay. Let's see here. So basically a general sort of idea is this, is you want to use the most simple thing that you can. You know, don't overcomplicate things unless you need to for some reason. So some of these simple things like minimax and decision processes, like they're relatively simpler, and so if you can get away with something just like if you can get away with just like a basic pathfinding algorithm, you know, don't make some like extra complicated thing, I guess. And I guess these two are also some things are used in combination as well. So yeah, so supervised learning. So another limitation, I guess, is the access to data, and especially labeled data. So a really good example of a supervised learning problem is the sort of handwritten digit recognition. So that's saying, I think it was a big deal because back in early 2000s or whatever, they had a lot of mail with like stuff written on it, and they wanted to be able to like automatically sort it without people having to manually, you know, check the thing, that sort of thing. So with supervised learning, if you already have a bunch of existing data and that you want to predict and use, let me go to the other slide so I can explain that a bit better. So yeah, so on this like right graph here, like imagine that you're trying to predict like the value of a house or something, and then the x-axis might be the number of, I guess that one, I mean, just say it's the number of like floors you have or something. You have like 1.5 floors on your house, I don't know. But then your y-axis could be the square footage of your house or something like that. So essentially with this, it's like if you'd already gone around and looked at some houses and the owners told you that, hey, you know, this house is valued this much, then you can make this sort of plot. So you already have this existing data about how, you know, you go to a house, you figure out the features, which is the number of floors it has, the square footage, and then its label, which would be the value of that house. But if you notice here, what if you have, you find a new house that you don't know the value of, and it has negative 1.5 floors, I don't know, and then it has negative 5 square footage, which also doesn't work. But anywho, that'd be that point right here. But look, you don't actually have any labels here, so you don't know what it is. And so the whole point of the supervised learning is you can make this sort of line here that regresses your data. And so then what you can do is say, well, hey, we don't know exactly what is here, but we know based on this line here that it should be about right here or something. So yeah, so use that if you have some data. And then unsupervised learning, that's if you have the same houses, but you don't know the value of any of them. And so you just want to see, well, hey, what are some different categories of houses? Maybe you have like rich people houses and like middle class houses, and then like poorer houses or something like that. And so you have all this like data or something like that, but you want to actually figure that out into the different categories. So let's see here. Also, I actually did a project here where I looked at people's Spotify music. And so for this one, it's actually a website. If you guys want to check it out, you can. But you can input like a playlist to it, and then it'll look at all your songs in your playlist, and it will try to derive different clusters out of it. And so if imagine these points represent your music on Spotify or something. So if it sees that you have one really big cluster of music here, that might be like one genre or something, but then you have a little cluster here, then we can maybe say, well, hey, these songs here don't really fit on your playlist because they're really not in the same clusters altogether. So you can kind of use it to make inferences about the data. Reinforcement learning. Do you want to talk about some of this?
So the two previous examples are kind of different from reinforcement learning because we didn't have like a single agent that was acting in an environment. Like with the houses, there's no really agent there, or with the Spotify playlist. So we can look at this example again. Any time where we have an agent in an environment, and it doesn't have to be like video games and stuff like this are a good example, but it could be like a robot or or like something in some sort of maze, or any time where there's a single sort of entity that is moving about in an environment, that's a good sort of way to know that reinforcement learning is going to be a good method for teaching that. Yeah, and especially when we've got an agent and we want it to learn some behavior, I guess.
Right, and another point in that too is that if you think about like the house example, there's only like you're only trying to predict like one thing, I guess. But with this, if it's on a walking or something, it's on a very continuous domain. So there's all these different points of data that if you were to use supervised learning, you need to collect so much data about how to move if it's at a certain angle, how to move if the angle is slightly changed. It's just unfeasible. So this one's good if again you don't have the label data, and then you kind of need to, but you kind of have an idea of what should it be doing, what should it not be doing, and how can I guide it to figure that out. And meta-heuristics, this can be, since this is a really broad category, it's a little hard to say, but, and I don't know everything about all the ant colony optimization stuff like that, but with genetic algorithms in particular, that can be used kind of similar to reinforcement learning in some cases, because again, it's like you don't know exactly how the stick guy should be walking, but you know that you want it to be on, alternating its legs, and you want it to be, moving to one direction or something like that. So this one's really good too if you have some sort of like agent again trying to do something, and you want to just kind of randomly make a ton of them and then be able to select and sort of randomly evolve that to a solution, I guess. Yeah, so is there anything else we need to talk about?
I don't think so. We can open up the questions.
Yeah, does anyone have any questions or comments? Yes?
What would be an example of AI that is not machine learning?
Right, so an example of that, if you go back to like the pathfinding, that sort of thing, say you want to make like a Google Map sort of app or something like that, and you want to, where you're starting at, and then where you want to end up at, and then the roads that are connecting it, you could deploy like a pathfinding algorithm to figure that path out, and then that would be AI. And then also like the minimax algorithm, so that can be useful for chess, because essentially you can look at your current state and then sort of make projections into the future possible states, and then sort of derive what the best next step is.
Yeah, it's kind of when you have a good idea of what needs to happen in all of your environments, so instead of having to learn how to do something, it's more just like intelligently do something.
Yeah, it's what it's called, that it's deterministic. So some of the models that we talked about are probabilistic, which means that there's some probability and randomness assigned with it. But yeah, with that, it's more deterministic.
Good question.
Yeah. Any other questions or comments or anything?
Yeah, I think future workshops are going to be more of a mix of like, we'll teach a topic, but then we'll also show like really applied versions of it, just to sort of give you guys an intro. We wanted to go over like as much AI stuff as possible, just to show you what is out there.
Right. So yeah, so this one is not necessarily like super helpful in teaching you guys specifically, hey, how do you do this, how do you do that? It's sort of like, oh, hey, here's exposure to like all these different topics. But in the future, we want to have like actual like tutorials and stuff where we say like, hey, let's live program something, and you guys can like follow along or something like that. But would that be something you guys are interested in, or?
Yeah.
Okay. Is there anything else you want us? Yes. Oh.
I just have a question.
Yeah.
Are there any particular resources or like places, like was anything past the curse of Google search, or do you guys have any sites that you like in particular for certain topics, like oh, like this is really good, or I know you can like Google, so I can find stuff, but anything you guys like in particular, certain sources?
I mean, to be honest, like I've just looked at a lot of YouTube videos. So there's a lot of good YouTube channels out there. I also, if you guys want to get more into it specifically, Daniel and I took a Coursera online certificate course thing like over winter break. It was just called Machine Learning. It was by Stanford. But there's some like sort of certificate course online things that are kind of chill, but they give you like a really good how to do this sort of thing. So that would be a good recommendation.
And Coursera's all free, right?
Yeah, you can do it all free. It's like you have to like pay if you want to get the certificate, but you can just do it for free.
And it's kind of directed at data science, but it has general machine learning stuff in general. I think it's called towardsdatascience.com. It's kind of a place where people just blog about all machine learning stuff. So a lot of times I don't really go there specifically to search stuff, but a lot of times when I'm like Googling how to do a certain thing in machine learning, like if I want to know like what the hell is DQ learning, a lot of times towards data science comes up.
Yeah, and then also I found a lot of, like, when I've been searching stuff up, like medium.com, also blog site, like I found some of their stuff to be useful. So yeah, is there anything else you guys want us to talk about right now? I mean, it's already been 45 minutes, so probably not, but yeah. All right, cool.
Well,
Well,
yeah, we
thanks
really
for
appreciate
coming.
all you coming on the weekend.
Yeah.
Yeah, thank you guys for hosting.
Absolutely.
Yeah, and if you guys have specific stuff, if you want to learn more about a specific topic, one, I encourage you sort of search it on your own if you want to learn about it quickly. Or two, if you found something in here especially interesting, just talk to us and we might make a workshop specifically on that.
Yeah, also, does anybody have any suggestions on how we can do a better workshop sort of thing? Like, you can be brutally honest.
I think a lot of these are like intangible to me because I'm pretty new. I don't know for everyone else, but maybe like I think you guys had really cool examples, but maybe something like I don't know how feasible / realistic it is, but something more interactive maybe that sort of thing.
Okay.
I think you guys did a pretty good job of listing a bunch of examples, but maybe some more interactive. Here.
Totally.
Definitely. Yeah. When we're going over specific topics, we're definitely going to have like.
Yeah, no, this is
here
like
is
more
some
general
code.
overview.
Yeah.
Mhm.
Cool.
I'll try to show up on time.
Well, have a good one, guys. Thanks for coming.
Yes, thank you guys.
Thank you guys.
And slides will be posted, and as long as this video isn't terrible, we'll post the video as well.
Yeah. Yeah. So